Welcome to Module 203C on Basic Gas-Fired Forced Air Heating Systems. We're going to be talking about what are called standard efficiency furnaces, which are between the 65 to 75% efficiency range, and these have typically been installed before 1992. We're going to discuss the basic operation of the furnace as well as a number of the basic parts. This module contains 5 different objectives that we'll go through one at a time. We're going to start with looking at the components in a basic gas-fired forced air heating system. In the last module, we discussed basic component groups of a furnace, such as the burners, the blower, the heat exchanger, and the flue. Now we're going to take a closer look at the specific parts that make up a standard furnace and how they integrate with everything else that we have. We're going to start with a thermocouple. A thermocouple is known as a flame-proofing device. Its job is to make sure that the furnace knows whether or not a pilot light is lit, so therefore it only works on appliances that have a standing pilot light. The thermocouple produces a small voltage when it's heated, anywhere between 26 and 32 millivolts. The job of the thermocouple is to provide power to the gas valve coil, also called the power unit. The power unit is a coil that creates an electromagnetic field that holds open the armature inside the gas valve. If I have no heat on the thermocouple, then the thermocouple will provide no power to the power unit and it will allow the armature to drop back into the closed position. When the thermocouple is heated, it will supply enough power to the power unit in order to hold the armature in place. However, it's not strong enough to actually move the position of the armature. That's why older furnaces require a manual reset button. In order to light a furnace or a hot water tank or anything with this type of system, we need to push down and hold the reset button while we light the pilot light. After the pilot light is lit and it warms up the thermocouple, then it provides enough power to the power unit to keep the armature in place. So then we can release the reset button. This is usually why we have to hold it for up to 30 seconds while that thermocouple heats up. The thermocouple has different jobs depending on the type of system that it is installed in. In early gas valves, like the one that you see on the screen, the thermocouple was wired up to the power unit, which controlled a set of contacts called the pilot safety switch. The pilot safety switch was then installed into the control circuit in series with the main gas valve. If we lost flame from the pilot burner, it would shut off the main gas valve, stopping any gas from leaving the main burner. A big disadvantage to this system is that there's no way to stop gas from escaping through the pilot valve. In order to address this, they developed the safety gas valve. The thermocouple's job now is to control the power going to the safety gas valve in order to hold that open. This is the type of system that would require that reset button we were talking about. We now have 2 different valves. The solenoid gas valve is controlled by the thermostat and operates the main burners. When the room calls for heat, this gas valve will open and allow gas through the main burners. However, if the pilot burner ever went out, the thermocouple would then lose power and therefore it would allow the safety gas valve to close. This shuts off all gas to the system, which would include the main burner and the pilot burner, and this gives us an extra safety step. Eventually, they combine both these gas valves together to create the combination gas valve. In this case, we have both the safety gas valve and the main gas valve in one unit. The thermocouple still powers the power unit, which still controls the main gas feeding the system. After the safety gas valve, we have a T that will feed the pilot burner as well as the main gas valve. The main gas valve is still being controlled by the thermostat in the wall and feeds gas to the main burner. This type of gas valve will have 2 different power supplies, the thermocouple as well as the thermostat connection. When it comes to the inner workings of the gas valves, we have 2 different types, the first type being the solenoid valve. The solenoid valve is considered to be a primary control device, and it is wired in series with the operating controllers, such as the thermostat and the limit switches. We would use this with a main gas valve. It uses a solenoid coil in order to create a magnetic field that pulls the plunger up when it is energized. This will open the gas valve, allowing gas to flow through. When the coil is de-energized and the thermostat is shut off, the plunger then drops back into place. It is very fast acting and works with the gas pressure as well, so the gas pressure helps keep the valve seated properly. The other type of valve that we have is called the diaphragm valve. Inside this particular gas valve, we have two different chambers. On the upper chamber, it is controlled by a plunger that is operated by the armature in the coil. As the plunger changes position, it will also change the gas pressure on the upper side of the chamber. When this valve is in the closed position, it means that the pressure of the main gas supply equals the pressure on top of the diaphragm as well. If I wish to change the position of the diaphragm, it means I have to change the pressure between the bottom and the top of this diaphragm as well. By energizing the coil, I move the armature, which moves the plunger. As soon as the plunger moves, it allows the gas in the upper chamber to bleed out. This means the main gas supply will now have enough pressure to push the diaphragm up and out of the way, opening the valve in order to allow gas through. When the coil is de-energized, the plunger moves back into its original position, allowing that upper chamber to refill with gas, balancing the pressure between the upper and the bottom side. This moves the diaphragm back down to its original starting position, shutting off the gas supply, and it remains there until we need gas to flow through there again. These are typically a lot slower in operation than the solenoid valves, simply because they are operated by that gas pressure difference. Our next components are blowers and controls. All forced air furnaces need to have a blower in order to circulate the air, and they can either be direct coupled, meaning the fan is directly connected to the motor, or they can be belt driven. Some of them can also be set up for two-speed operation, whereas the lower speed keeps temperatures balanced throughout the building, and the higher speed engages when the burners are on in order to cycle the warmer air. Some of the maintenance concerns we would have is to change out the belts and also to grease any bearings that might require it. The blower is operated by the fan control, which is set on the plenum temperature. The fan on and the fan off settings of the fan control are based on the comfort levels inside the building. The fan on setting should be anywhere between 49 degrees and 60 degrees. When it comes to the fan off setting, we don't want it to be too close to the fan on, otherwise it could produce premature cycling, which would wear out our furnace quicker. We want to make sure that we have a differential of between 17 and 22 degrees between my fan on and my fan off. Remember that when the fan turns on, it is mixing the cooler air of the building with hot air inside the plenum, which will significantly drop the temperature of the plenum. So we have to be aware of that when we set our fan off settings as well. Our blower fans can also be operated by other devices, such as our air conditioning relay contacts and our manual override switch, or our summer switch. They are all wired in parallel to the fan contacts. You have now reached the end of this objective. Review your module, complete the knowledge check, and then continue on to the next video.